Let's look at 2018 AP Physics 1 free response question. Number 1 looks like orbit. Let's see. You have a spacecraft, mass m, small m, in clockwise circular orbit, so it's like that. A radius r around Earth. So r is the whole distance. And mass of Earth is me, so capital M. The figure below drew and labeled the forces that acts on spacecraft. Well, the only force is force of gravity, right? Yeah, I'll solve it first, and I'll explain like a little bit deeper into this. So let's see, derive equation for orbital period. It's basic derivation. So force of gravity. Here you can't use mg anymore because g only works in surface on Earth, right? So you can't use this anymore. This is the short form. So you have to use the original form of gravitational force, which is g mass of Earth and mass of here satellite, use small m, over, this is radius. It's actually distance between center of Earth to center of spacecraft. And here they use the whole thing as r, so you don't have to really worry about. So this is r square. But for the side note, a lot of times you'll see like they give radius of Earth and you have height of h and then this satellite orbit. In this case, you have to use this r as re, radius of Earth, plus height above. You have to replace that into this r. But for this problem, they get the whole r as the distance between center and center. Now, this equals, in fact, it's F equals ma, or a net if you want to say, which is true. This has to be ma net, which equals ma net. But in this scenario, this a net is actually a centripetal acceleration, right? Because there's no tangential acceleration. This a net is just ac, so it's basically mac, which basically equals mv squared over r. This is for centripetal acceleration. Okay, so now this becomes there. Oops, it's hiding there, so I'll change that. So again, so force of gravity, which equals ma, which equals mac in this scenario, which is mv squared r. Okay, now you want orbital periods. So here basically you have to play with velocity. Okay, so velocity in this expression, you can write this velocity as distance traveled over time, but this distance traveled, you can use circumference, and time it takes to rotate one's circle is what period. That's what you're looking for. Okay, so basically you have to replace this v into here as 2 pi over t, then you have to isolate t. Okay, again, it's hiding there, so I'll just move it like that. Maybe I have to change my camera. All right, actually I'm gonna hide it. All right, now let's solve it now. So you get g me over m over r squared equals m v squared over r. I'm not gonna plug it right now because this is a little too messy, so let me simplify first. Again, here mass of satellite does not change, and r, you can cancel one of them. So first I get v squared as g mass of Earth over r. Okay, and a lot of times you'll need this expression because the significance of this equation is the orbital speed does not depend on mass of the satellite. Okay, this only depends on mass of the center star, or in this case mass of Earth in this problem, because the reason is because you cancel this mass on both sides, so your velocity does not depending on mass of the satellite. Okay, now for this problem you have to replace this by 2 pi r over t. Again, you'll get another interesting derivation there. So if you replace v, you get 4. Make sure you square all of them, okay? So you get 4 pi square r squared over t squared equals g mass of Earth over radius. And I'll multiply r on both sides and divide by 4 pi square. So I multiply r, then this becomes cubic, this becomes r cube. So I'll just write r cube. Then if you divide by 4 pi square, you'll get gme over 4 pi square. And if you flip this, you get t squared over r cube equals 4 pi square over gme. You may argue like, why'd you do this one instead of solving t? Because this is actually Kepler's third law. Okay, so you have t squared over r cube is actually constant. The reason it's constant is because 4 constant, pi constant, g constant, mass of Earth constant. So right side is constant, so left side is constant. So this is actually the proof of Kepler's third law. And if you want to solve for t, you have to multiply by r cubed. So t squared equals 4 pi square r cubed over gme. And you can solve for t as square root of that. Right, so that is the period. Now, the second spacecraft of 2M placed in a circular orbit is the orbital period second greater, less than, or equal. This I already explained, because on top, the orbital speed was this, or orbital period. So basically, orbital period was this, and there's no mass for spacecraft. Okay, make sure you understand this is mass of Earth. Okay, it's not, it's so basically if something is orbiting, the period or speed of this guy depending on whatever mass who is at the center, not mass of itself. Okay, so that's the key point here. So here will be equal to, and you can say using this equation if you wanna. All right, and last question, last part. The spacecraft will move into new circular orbit that has radius greater than r. Is the speed of spacecraft do orbit greater or less than or equal? So I'm pretty sure it's less than. And here we're talking about speed. And actually I already derived this equation for speed, which is this, right? Which is, I'll just write one more time. V squared equals g me over r, or you want to say v is radical gme over r. So it has nothing to do with actually a mass of satellite, but it has to do with the orbital radius, right? So if r gets bigger, obviously the velocity gets smaller, so that's why it's less than. Okay, and